In this lecture, let me give you some examples for evaluating the electric field due to some charges or charge distribution. Let's consider the simplest case, an electric field produced by a point charge as shown in the figure. The point charge establishes an electric field at all points surrounding it. This is the effect of the source charge on space. We put a test charge Q0 into space to determine the electric field vector. According to Coulomb's law, the force exerted by Q on the test charge is this one, where R hat is the unit vector directed from the source charge Q toward the test charge Q0. Based on the definition of the electric field at point P created by Q can be calculated by this one. What information can we have from this equation? Let's check the magnitude of the field first. The magnitude of the field is proportional to the source charge and inversely proportional to the square of the distance between the source charge and the point of interest. When the point is located at infinity, the field is zero. This equation also indicates that the electric field is the same in magnitude at all points at a distance r from the source charge. Consider a spherical surface with radius r concentric with the source charge. The magnitudes of the fields everywhere on this spherical surface are identical. Secondly, let's examine the direction of the electric field from this equation. We can see that the direction of the electric field is radially outward if the source charge is positive and radially inward if the source charge is negative, as shown in this figure. If two more point charges present, how to determine the electric field? An electric field is a vector quantity. We can apply the superposition principle to calculate the resultant field due to a group of charges. At any point P, the total electric field due to a group of source charges equals the vector sum of the electric fields established by all the charges individually, given by this equation, where Ri is the distance from the ith source charge Qi to the point P, and Ri hat is the unit vector directed from Qi toward point P. Let's see an example. Please evaluate the electric field created by an electric dipole. What is an electric dipole? Please see this figure. It's a model composed of two charges of equal magnitude and opposite signs. These two charges are separated by R0. We could apply a vector quantity P, called electric dipole moment, to describe the electric dipole. The electric dipole moment is directed along the line joining the charges from minus Q to plus Q. It's defined by this formula. Okay, let's return to the problem. Firstly, please find the electric field at point A along the line joining the two charges. By applying the superposition principle, the total electric field at point A equals the vector sum of E plus and E minus, where E plus is the field due to the positive charge plus Q, and E minus is the field due to the negative charge minus Q. Hence, the resultant electric field is expressed by this one. From this expression, we can see that when X is much larger than R0, which means point A is very far away from the dipole, the magnitude of the electric field is inversely proportional to the cubic of the distance. Next, please find the electric field at point B along the perpendicular bisector of the line joining the two charges. Please note, E plus and E minus have different directions in this case. By considering the symmetry of the situation, the y components of E plus and E- cancel as shown in the figure. Therefore, the resultant electric field at point B must be directed to the left, which is parallel to the x-axis. We calculate the electric field due to the positive charge and negative charge individually. The resultant field at point B is the vector sum of all contributions from these two charges. The details on the calculating are shown here. In some cases, the distances between charges in a group of charges may be much smaller than the distance between the group and a point of interest. In this situation, the system of charges can be modeled as continuously distributed along some line, over some surface, or throughout some volume. Next, I will show you how to evaluate the electric field due to continuous charge distribution.